The undersea tunnel, where compasses stop working. What's hidden beneath? Did you know there's a tunnel beneath the ocean where your compass just stops working? No north, no south, just spinning needlessly, as if the Earth's magnetic field vanished. Engineers driving through it for the first time reported their navigation systems going haywire, screens flickering, GPS signals dropping, instruments reading impossible directions. But that's not even the strangest part. This tunnel connects two nations separated by one of the most dangerous stretches of water on the planet, where over 2,000 ships sink every year and massive whirlpools can swallow vessels whole. But here's what engineers don't want you to know. The tunnel passes directly through an area where tectonic plates are grinding together, and one major earthquake could trap thousands of people 140 meters underwater with no escape route. So how exactly did they build something so dangerous? And what happens when those plates finally shift? If you're fascinated by engineering marvels like this, make sure to hit that subscribe button and ring the notification bell. We dive deep into the world's most incredible projects every week. The Seismic Tunnel in Japan isn't just any underwater passage. It's humanity's answer to one of nature's deadliest challenges, the Tsugaru Strait. For centuries, this 54-kilometer stretch of water between Japan's main island of Honshu and the northern island of Hokkaido was a graveyard. Ferry after ferry disappeared into its depths, claimed by typhoons, whirlpools, and waves that could reach 10 meters high in minutes. The breaking point came on September 26, 1954. 5 ferries sank in a single typhoon. Over 1,400 people died in just one day. Entire families wiped out, students who never made it home. The Japanese government realized something had to change. This maritime cemetery needed a solution that defied everything engineers thought possible. Talks of an undersea tunnel dated back to the 1940s, but everyone said it couldn't be done. The strait was too deep, the rock too unstable, the water pressure too extreme. Political will kept dying along with the funding proposals. Engineers drew up plans, politicians rejected them, and more ferries kept sinking. That changed in 1964 when the Japanese government finally approved the impossible project. Construction began in 1971, and what followed was 17 years of battling nature itself. They weren't just digging through rock, they were tunneling through waterlogged zones where seawater gushed in at 80 tons per minute. Workers died. Equipment failed, costs exploded from $361 million to over $3.6 billion. The technical challenges seemed designed to stop them. The tunnel needed to go 140 meters below the seabed at its deepest point, deeper than any rail tunnel ever attempted. The Tsugaru Strait sits where two tectonic plates meet, meaning earthquakes are constant. The rock formations were fractured, porous, and unpredictable. One day you'd be digging through granite, the next you'd hit a pocket of water-saturated volcanic debris that would collapse without warning. But Japanese engineers had something driving them beyond technical ambition. They remembered those 1,400 bodies. Every setback, every flood, every worker lost only made them more determined. They developed new tunneling techniques, invented waterproofing methods that didn't exist, and created drainage systems that could handle impossible volumes of seawater. By 1983, after 12 years of digging from both ends, the two tunnel teams finally met 140 meters under the ocean. The breakthrough moment was millimeter perfect, a testament to surveying accuracy that borders on supernatural. 4 more years of laying track, installing systems, and reinforcing sections, and on March 13, 1988, the Seismic Tunnel finally opened. It immediately became the world's longest undersea tunnel at 53.85 kilometers total length, with 23.3 kilometers actually under the seabed. That record stood for 30 years until the Gotthard Base Tunnel took the crown. But the Gotthard goes through a mountain, not under an ocean. The Seismic remains the deepest undersea tunnel and the longest undersea section ever built. What do you think about this ambitious vision? Drop your thoughts in the comments below. I read every single one. And if you're enjoying this deep dive, give this video a thumbs up to help others discover these incredible projects. The Seismic Tunnel isn't just a hole under the ocean, it's an underground city designed to survive disasters. The main tunnel is 11.5 meters in diameter, wide enough to fit a 2-story building. But here's what most people don't know. It's actually 3 tunnels. The main passage carries the trains. 23 meters below that runs a service tunnel where workers maintain systems and respond to emergencies. and connecting them every 600 meters are escape shafts, because if something goes wrong 140 meters underwater, you need a way out. The tunnel handles both freight and passenger trains, including Japan's famous Shinkansen bullet trains. These trains were modified specifically for this tunnel, capable of traveling at 140 kilometers per hour through a passage where air pressure changes can rupture eardrums if not carefully controlled. The trains are designed with pressure-sealed doors and ventilation systems that equalize air pressure gradually as they descend and ascend. 4 massive vertical shafts connect the tunnel to the surface. 2 on the Honshu side, 2 on Hokkaido. The deepest shaft, Yoshioka, plunges 240 meters straight down. These aren't just access points, they're the tunnel's lungs. Enormous ventilation systems push fresh air through the tunnel at 60 cubic meters per second, preventing carbon monoxide buildup and keeping temperatures bearable despite the geothermal heat from being so deep underground. Now here's where the compass problem comes in. The tunnel runs through rock with such high iron content and unusual magnetic properties that traditional compasses become useless. The Earth's magnetic field gets distorted by iron ore deposits. Engineers had to install their own guidance systems because natural navigation simply doesn't work. The tunnel's drainage system is equally impressive. It has to be. Over 24 tons of seawater seep through the walls every single minute. That's 34,000 tons per day. A network of pumps running 24/7 evacuates this water through the service tunnel and up the vertical shafts. If those pumps failed, the tunnel would flood completely in less than 14 hours. Safety systems are redundant beyond redundancy. Fire detection sensors every 50 meters. Emergency lighting powered by independent backup generators. Communication systems that work even if the main power grid fails. Seismic sensors that can detect earthquake tremors and automatically stop trains. The tunnel has survived dozens of major earthquakes, including the 2011 Tohoku earthquake that measured 9.1 and triggered the Fukushima disaster. While the world above was being destroyed by a tsunami, trains in the Seikan tunnel stopped safely and passengers were evacuated without a single injury. The tunnel also features 2 undersea stations, Tapi Kaitei on the Honshu side and Yoshioka Kaitei on the Hokkaido side. These aren't passenger stations anymore, but they serve as emergency evacuation points and museum exhibits where visitors can experience being 140 meters under the ocean floor. You can actually take a tour and stand in a tunnel while ships sail overhead. Technology integration includes automated monitoring systems that track everything from air quality to structural integrity in real time. Fiber optic sensors embedded in the concrete detect microscopic cracks before they become dangerous. Thermal imaging cameras monitor for hotspots that might indicate electrical problems. The tunnel essentially diagnoses its own health and reports problems before humans even notice them. The revolutionary feature that often gets overlooked, this tunnel connected Japan's rail network in a way ferries never could. Before Seikan, you had to load entire trains onto ferries, cross the strait, and unload them. Now freight trains carrying everything from cars to electronics move seamlessly between the islands, making Japan's logistics network truly unified for the first time in history. The scale of this project is mind-blowing, but wait until you hear about the massive investment behind it. Before we dive into those numbers, which feature impressed you the most? Let me know in the comments. The Seikan Tunnel's final price tag hit $3.6 billion in 1988 dollars. That's roughly $9.2 billion in today's money, but the real cost was far higher when you factor in 17 years of labor, 34 workers who died during construction, and the countless injuries and setbacks that aren't captured in financial reports. The Japanese government funded this almost entirely through the Japanese National Railways, which later became the Japan Railway Companies after privatization. There was no private investment. This was considered too risky and too important to leave to private companies. The government absorbed the entire financial burden because connecting Hokkaido to the main island was viewed as a national security and economic necessity. But here's the brutal truth. Engineers don't advertise. The tunnel has never been profitable. Operating costs for ventilation, pumping, maintenance, and staffing run approximately $150 million per year. Revenue from train tickets and freight fees doesn't come close to covering those costs, let alone repaying the construction investment. To put the cost in perspective, $3.6 billion in 1988 was more than Japan spent on multiple airports, highways and ports combined that same year. It was equivalent to building 60 kilometers of Tokyo subway lines or constructing 10 modern hospitals. The Japanese government chose this tunnel over countless other projects because the human cost of ferry disasters was unacceptable. The economic multiplier effect extended beyond the tunnel itself. Japan had to upgrade rail lines on both sides, improve connections to regional networks, and modernize freight handling systems. When you add all the supporting infrastructure, the total investment easily exceeded $6 billion. The value justification was never purely financial. It was about lives saved, economic integration, and national pride. Since 1988, 0 people have died crossing the Tsugaru Strait by rail. Compare that to the thousands who died on ferries, and suddenly $9.2 billion seems like a bargain. The Seikan Tunnel opened on March 13, 1988, and has been operational for over 36 years now. But the story doesn't end with the ribbon-cutting ceremony. Maintaining this engineering marvel is almost as challenging as building it was. The major construction milestone came in 2016, when Japan extended its Hokkaido Shinkansen line through the tunnel. This required massive upgrades because the original tunnel was designed for conventional trains traveling at moderate speeds. Allowing bullet trains traveling at 140 kilometers per hour required reinforcing sections, upgrading power systems, and implementing new signaling technology. The modification project cost an additional $800 million and took 3 years of careful work while keeping the tunnel operational for freight trains. Engineers essentially performed surgery on a tunnel 140 meters underwater without closing it. They worked during narrow maintenance windows at night, installing new track beds, upgrading electrical systems, and reinforcing sections that would experience higher stress from faster trains. Key contractors involved include Obayashi Corporation, Kojima Corporation, and Taisei Corporation, Japan's largest construction firms. These same companies built the original tunnel and have remained involved in its maintenance and upgrades. The continuity matters because institutional knowledge about the tunnel's quirks and vulnerabilities is passed down through decades of experience. Current progress metrics show the tunnel operating at approximately 85% of its designed capacity. About 50 trains pass through daily, a mix of freight and passenger services. That number is expected to increase to 70 trains per day by 2030 as Hokkaido's economy grows and freight traffic expands. The coordination complexity cannot be overstated. Every train movement must be precisely scheduled because there's only one track for most of the tunnel length. Freight trains traveling at 80 kilometers per hour share the space with bullet trains traveling at 140. The signaling system must prevent collisions, manage air pressure changes, and ensure that slow-moving freight doesn't create bottlenecks for passenger services. Testing and commissioning never really ends. Every 6 months, the entire tunnel undergoes a comprehensive inspection. Engineers use specialized cameras to examine every meter of wall surface, checking for cracks, water infiltration, or structural degradation. Robotic systems crawl through sections too dangerous for humans, measuring concrete thickness, checking rebar integrity, and detecting early signs of deterioration. The tunnel's major milestones include surviving the 2011 Tohoku earthquake without structural damage, handling record freight volumes during the COVID-19 pandemic when air cargo was restricted, and achieving 35 consecutive years without a fatal accident, a safety record unmatched by any comparable infrastructure project. Recent upgrades include installing 5G communication systems throughout the tunnel, allowing real-time data transmission and remote monitoring. Engineers in Tokyo can now watch live feeds from inside the tunnel, spot problems instantly, and dispatch maintenance teams before minor issues become major failures. The Seikan Tunnel's greatest enemy isn't human error, it's geology. The tunnel sits directly on the boundary between the North American plate and the Eurasian plate. These tectonic plates are grinding together at about 8 centimeters per year, generating constant seismic activity. Japan experiences over 1,500 earthquakes annually, and the tunnel feels many of them. Each earthquake creates microscopic cracks in the concrete, gradually weakening the structure despite all the reinforcement. Water infiltration remains the biggest ongoing challenge. Remember those 24 tons per minute seeping through. That number is increasing. When the tunnel first opened, it was 20 tons per minute. The gradual increase suggests the waterproofing is slowly deteriorating, expected after 36 years, but concerning nonetheless. If infiltration reaches 40 tons per minute, the pumps might struggle to keep up. Financial criticisms are impossible to ignore. The tunnel loses money every year. Some economists argue that Japan should have simply improved ferry services or invested in air travel infrastructure instead. The counter-argument, how do you put a price on 0 deaths, doesn't satisfy critics who point out that those billions could have funded healthcare, education, or earthquake-resistant housing that would save lives in other ways. Environmental concerns emerged during construction, and persist today. The tunnel disrupted underground aquifers, altered subsurface water flows, and potentially affected marine ecosystems above. Some studies suggest that pumping 34,000 tons of slightly warmer water out of the tunnel daily changes local ocean temperatures by measurable amounts. The long-term impact on fish populations and marine life remains unclear. Political opposition centered on Hokkaido's declining population. Critics asked why Japan spent billions connecting an island that people are leaving. Hokkaido's population peaked in 1997 at 5.7 million and has been declining ever since. Now it's around 5.2 million. Building expensive infrastructure to an island losing residents seemed economically backwards to many politicians. Technical obstacles that engineers still wrestle with include the tunnel's aging electrical systems. Much of the original 1980s technology is obsolete, requiring custom-made replacement parts that cost exponentially more than modern equivalents. Upgrading to current standards would require shutting down sections for extended periods, something Japan's logistics network can't easily accommodate. The risk factor everyone whispers about but rarely discusses publicly. What happens during a major earthquake if a train is in the tunnel? The 2011 earthquake proved the tunnel can survive massive seismic events, but that was luck. The earthquake's epicenter was far enough away that shaking was reduced by the time it reached the tunnel. A direct hit from a magnitude 8+ earthquake centered on the Tsugaru Strait could potentially collapse sections, trapping trains and passengers 140 meters underwater with limited rescue options. Social issues include accessibility concerns. The tunnel's high-speed focus means fewer stops and less service to rural areas along the route. Small communities that relied on ferries for local transport now have limited options. The tunnel serves major cities efficiently, but isolated rural Hokkaido further. Contingency plans exist but have limitations. Emergency evacuation procedures assume people can walk through the service tunnel to the nearest vertical shaft, but that could mean walking 5 kilometers in pitch darkness, while water seeps through the walls and aftershocks continue. Rescue simulations revealed it could take 6 to 8 hours to evacuate a fully loaded passenger train from the deepest section. Despite every criticism, the Seikan Tunnel fundamentally transformed Japan in ways that justify every yen spent. The most obvious benefit is the one that matters most: 0 deaths. In the 36 years since opening, millions of people have crossed the Tsugaru Strait safely. Compare that to the ferry era's death toll, and the tunnel becomes invaluable. Economic benefits extend far beyond ticket revenue. Hokkaido's agricultural products now reach Tokyo markets overnight, instead of waiting days for ferry schedules. Fresh seafood, dairy products, and produce arrive faster and in better condition. The tunnel enabled Hokkaido to compete in markets that were previously inaccessible due to transportation time. This integration boosted Hokkaido's GDP by an estimated 8% in the first decade after the tunnel opened. Job creation was massive during construction. Over 13,000 people worked on the tunnel at peak construction periods. Today, about 800 people work full-time maintaining and operating the tunnel, plus thousands more in supporting industries like rail maintenance, freight logistics, and tourism. Social improvements reshaped how Japanese people view Hokkaido. Before the tunnel, Hokkaido felt disconnected, almost like a separate country. Now it's a 4-hour train ride from Tokyo to Sapporo via the Shinkansen. That psychological shift matters. Young people are more willing to move to Hokkaido for work, knowing they can return home quickly. Businesses invest in Hokkaido operations, knowing supply chains are reliable. Technological advancement showcased Japan's engineering prowess to the world. The Seikan Tunnel put Japanese construction companies on the map for undersea infrastructure projects globally. Japanese firms now win contracts for underwater tunnels in South Korea, Taiwan, and Europe based largely on the reputation they built with Seikan. Regional development transformed both coastlines. The towns of Tapi on Honshu and Shirakami on Hokkaido became minor tourist destinations because of the tunnel. People visit specifically to see the entrance portals and tour the undersea stations. It's not massive tourism, but it brought economic activity to areas that were economically stagnant. Global significance is reflected in how often the Seikan Tunnel appears in engineering textbooks and documentaries worldwide. It proved that undersea rail tunnels at extreme depths were possible, inspiring projects like the Channel Tunnel between England and France which opened 6 years after Seikan and used Japanese engineering expertise. The long-term legacy might be environmental. Japan is now studying carbon-neutral freight transport through the tunnel, potentially using it to move goods between islands using electric trains powered by renewable energy instead of diesel ships burning bunker fuel. If successful, the tunnel could become a model for reducing maritime shipping emissions. Strategic benefits are rarely discussed, but critically important. The tunnel makes Japan's transportation network more resilient. If a major disaster shut down ports or airports, the tunnel provides a backup connection between the islands. During the COVID-19 pandemic, when air travel was restricted, freight continued flowing through the Seikan tunnel without interruption, keeping supply chains alive. The innovation showcase extends to safety technology. The seismic monitoring systems developed for the Seikan tunnel are now standard in earthquake-prone regions worldwide. The pressure equalization technology for trains has been adapted for other tunnels. The remote monitoring systems pioneered at Seikan influenced infrastructure management practices globally. The Seikan tunnel's future centers on one ambitious goal: increasing speed without sacrificing safety. Engineers are currently studying whether trains could eventually travel at 200 kilometers per hour through the tunnel, cutting travel time between Honshu and Hokkaido to under 3 hours. This would require billions in additional upgrades, but the economic benefits could finally make the tunnel profitable. Expansion phases include plans to widen sections to accommodate larger freight containers. Global shipping is moving toward bigger containers, and Japan's rail network needs to adapt. Widening even portions of the tunnel 140 meters underwater would be extraordinarily complex and expensive, but planners are seriously considering it for the 2030s. Climate change presents both threats and opportunities. Rising sea levels increase water pressure on the tunnel, accelerating wear and requiring more aggressive maintenance. But climate concerns are also driving interest in rail freight as a lower carbon alternative to ships, potentially increasing tunnel traffic significantly. Global implications are profound. Countries around the world are watching Japan's experience with the Seikan tunnel as they plan their own undersea connections. China is considering an undersea tunnel to Taiwan. South Korea and Japan have discussed a tunnel under the Korea Strait. Indonesia is planning undersea tunnels between its islands. The lessons learned from Seikan, both successes and failures, guide every one of these projects. Legacy prediction: the Seikan tunnel will be remembered as the project that proved humanity could conquer one of engineering's final frontiers: deep undersea rail connections. It wasn't the longest tunnel or the most expensive, but it was the first to go this deep under an ocean, through such challenging geology, in such a seismically active zone. Every undersea tunnel built after Seikan owes it a debt. The technological advances pioneered at Seikan, remote monitoring, seismic-resistant design, pressure management, advanced waterproofing, became industry standards. The tunnel's influence extends far beyond Japan's borders. Historical significance grows with time. When the Seikan Tunnel opened in 1988, it was seen as an impressive but risky project. 36 years later, after surviving the 2011 megaquake, after transporting millions of passengers safely, after proving skeptics wrong year after year, it stands as one of the 20th century's greatest engineering achievements. The compass anomaly that gives this tunnel its mystery is just one small quirk of a project that defied everything nature threw at it. Engineers built a tunnel where geology said it was impossible, through water that shouldn't be controllable, in an earthquake zone that should have made it unfeasible. And it works. Every day, trains pass through 140 meters under the ocean, through rock that plays havoc with magnetic fields, carrying people who probably don't even think about the engineering miracles surrounding them. That's the ultimate success, when impossible becomes routine. What's your take on the Seikan Tunnel? Do you think it's worth the ongoing costs, or should Japan have stuck with ferries and air travel? Would you ride through a tunnel where compasses don't work and earthquakes are constant? Share your thoughts below. I love hearing different perspectives. And don't forget to check out our video on the channel Tunnel's Hidden Secrets right here. Thanks for watching, and I'll see you in the next one.